I'm David Stumpf. I'm a emeritus professor at Northwestern University, had a research career with genetic diseases. I've been a lifelong genealogist, and really most of my career have done a lot of data analytics. So to talk today is about graphs for genealogists. You can start by just stating the obvious that graphs are everywhere. We have our social networks, power grids, airline routes, the stock market, the weather, and of course, relevant today, our family trees and our genes. So Graphs for Genealogists is a software package that tries to make your migration to using graph analytics easy. You're going to be able to use your standard genealogical data, stuff you're familiar with, and then have kind of a step-by-step guide of how to get that data into a graph database, download some applications that will allow you to get some quick successes with the analytics. There is a set of videos that's available at this particular link down here. I can't cover everything in this session today, and I'm going to try to make this not too heavy on the technical stuff and focus more on what Graphs for Genealogists does for you and what its benefits are. The slides for this will also be available, so you don't need to take a lot of notes and things like that. You should have these shortly after the meeting. So I'd also like to invite people into this project. It is an open source project, and there's lots of opportunities for people to get involved. And again, that same link can go to and take a look at what you might be interested in, and I hope some of you are at the end of this. Now, I've been doing data analytics for many, many years, and I want to take you briefly through a journey, which I'm sure many of you have been on as well. When I was in high school, the codicil data model was first introduced and had these basic requirements. The first iterations of this were with relational databases, some of which are mentioned here, which used tables and joins, which they called relationships. But in terms of graph theory, this is not what we're talking about today. Recently, we had the introduction of NoSQL databases. They got rid of the tables and instead focused on scanning efficiency to find key value pairs. The most recent developments have been with native graph databases. They elevated relationships to really first-class citizens. They deploy nodes, relationships, and properties. They introduced the first-time graph traversals instead of the joins that we typically had before or the scanning. They have an advantage of having little performance change when you scale up with more graphs or more data. And generally, the databases are half the size of relational databases. There's one other key aspect of this transition, if you will. The emphasis of these first two graph types was on data management. With the graph databases, the emphasis really shifted to data retrieval. That's a big advantage, but it does come with a bit of a cost. It makes the data management actually a little bit more difficult with these. So you're going really for the speed of retrieval here. Now, in those years I've been working in data management, I kind of grew up in the school of hard knocks, if you will. I've worked with many graphs in genealogy, and all of those are within scope for the Graphs for Genealogy project. Here are some of the challenges that I identified in my earlier work. The relational systems that we have commonly used in the past are not graph friendly. So you have to do lots of finagling to really get to what you want. Matrix systems did offer some improvement, but things like auto clusters, they really are sparse matrices. So in my auto cluster, I have like 3 million cells, and most of them are empty. If you use this same strategy with the larger data sets that we're managing now, I would have 62 trillion cells. So that really is computationally untenable. So the other problem I confront, of course, is that graph methods have generally been unavailable to genealogists. That's one of the principal problems this is trying to address. In doing that, you have to be, because we're bringing in data from multiple places, you really have to put a lot of emphasis on provenance of the data. And that's one of the major things that this project is focused on to date. There's several graph databases. The one that I have settled on is Neo4j for several reasons. It really is a market leader, open source. It's free when you're using the community edition. For us as genealogists, many of us will run this on a local server, although it can run in a cloud server as applications might be developed. It supports multiple programming languages, and you can access it either through an API or directly interfacing with the database. And for the people managing it, there are several other advantages which we won't get into today. So a graph database has nodes and relationships. These terms are from graph theory. Neo4j uses the node and relationship term. Each of these nodes and relationships can have properties, and those properties can be indexed. So we have the usual data types that we see in earlier systems, but in graph databases, we introduce new data types, the nodes and relationships, paths, and lists. When you start aggregating data, it does the usual things like counting and summing and averaging, but we now have traversals and collect and reduce, which we're going to talk about in just a minute, which are novel to a graph database. So what kind of data are we bringing into the graph? First of all, we're dealing with multiple kits. And this project is confined to family tree DNA data. We're bringing in family finder, chromosome browser, and then the genealogist needs to curate a couple of files, one which links the kits to the GEDCOM. That's covered in some of these videos. And the other one is an initial set of triangulation groups. We also bring in reference data like the HapMap and Y-haplotree and the shared Cinnamon project data. So graph querying also is different than SQL queries. It uses the GQL standard. On top of that, Neo4j has built what they call the cipher language, and it's designed to be intuitive. And you're going to see some of that today, so I want to make you familiar with the nodes are typically in parentheses, like person here. Relationships are in square brackets, like here, father. And the properties are in curly brackets, here, a record number for one of my ancestors. These queries generally will have a return statement. In this case, we're returning for P, person, the full name. So here's an example that would be very familiar to you and hopefully is intuitive. So we're finding a path starting with a person, in this case, me, record number 1, that's a property of person. We're traversing my father and mother graph, 3 hops, and finding the ancestors who we return then as a path. So here I am, and here are the paths to my great-grandparents. So this hopefully does end up being pretty intuitive for you. This is also an introduction to graph traversals. So the way they actually work is they use the index to find the start node, in this case, my great-grandfather, and then they traverses the relationships. Here, we're doing just a father for 3 hops, 1, 2, 3. So we're going back 3 generations there. And then we would return, in this case, the path itself. This is a technical slide coming up. I don't want to get overly technical here, but I do want to point out how a couple functions work. There's 3 examples here dealing with the path. The first line, the match line, and the return line are the same in all 3 examples. The difference here is in the middle part. And here you can see that we're collecting full names with the path also in this with statement. This is somewhat analogous to group by, if you're familiar with SQL query language. Here, though, we're collecting directly. And what this returns is a list of strings. In this case, the ancestors all lined up in their order in the path. The reduce function begins by defining the data type, in this case, a string, then iterates through the nodes in the path and adds the name each step of the way. So here we see 4 rows with a sequential building of the path. This is a list of strings that it produces. So this function is particularly helpful to genealogists. And let me give you a specific example of that. Here we're using the reduce function and the gender of the ancestors in the path to create a concatenated bit string, which ends up being the base 2 of the Ahnentafel number. There now we'll introduce another function here. This is one of the user-defined functions that converts this base 2 number to base 10 to produce for us the familiar Ahnentafel number. So what is a user-defined function? So Neo4j supports what they call plugins, and these are basically Java-coded functions and procedures. The advantage is they run directly against a server, so they're much faster. And they also, of course, because we can code these, we can get a lot more flexibility and do things that are not intrinsic to Neo4j. So Neo4j itself has done that. They produced a couple of useful plugins called APOC and GDS, which are actually used in the Graph for Genealogy plugin as well. We haven't yet implemented the spatial in the genealogy functions. So Graphs for Genealogy is a plugin, and it has a set of user-defined functions that are specifically designed to manage genealogical data and the analytics. Currently, there are 123 functions in there. That will grow over time. It is open source. You can pull it down from GitHub if you're so inclined. But one of the advantages of this is going to enable collaboration and development by other people as well. So that's part of the strategy of using this method. That really is the motivation here. We want to make success easy for genealogists, so you don't have to know a lot about graph analytics to start down this road. It is really quite easy to load your data, which you're familiar with, and then the database has a very robust schema. A lot of the time in this effort was spent on optimizing that schema. So then there's another application, a small application that allows you to use menus to get out lots of different kinds of reports. The main focus of this is discovering actionable insights for you. We want to get, clues that you can then take back to your traditional genealogical research. The reports will, as you'll see an example of, have some data, but also some educational information. Most of them also have the actual query, so that you can see what's going on and you can begin to experiment with these queries. So this is designed to help you kind of get more and more familiar progressively with graphs. And it also tries to get you to think in graphs. And graph thinking is one of those concepts that we struggle with educating people about. See, the other advantage of these functions is that they're modular, so they can be reused. And we'll show some examples of how that works. This also provides scalability and encourages other experts to participate. If you're an expert in something that's not there, you might be able to develop that. So how does this simplification look? Well, here's an example of a cipher query, which will produce a report that is somewhat like the Ancestry through lines. And you don't have to know this or know how to do this. All you do in Graphs for Genealogy is enter this simple phrase and hit the go button and you get a report. And in fact, in the software, this is menu driven, so you don't even have to enter this. So that's the level of simplification that goes on in this. Let me give you another specific example of that with the X chromosome. Here's a function. The gen here is how you address the Graphs for Genealogy plugin. And then you have the query name, and many of the queries will accept a parameter. In this case, it's my great-great-grandmother's record number in the GEDCOM. And this report actually then produces an output in Excel with 5 different worksheets. It shows the X ancestors that may have contributed an X chromosome. It then has a descendancy chart, which is excluding, as is this, the male-to-male transmission. And it then gets all of the X chromosome relatives, whether they're ancestors or descendants. And then it does some things that help you determine who in your data set had testing, who would be a candidate, who has an X chromosome match. So here's an example of the output you get. This is the ancestors of my great-great-grandmother. Going back, these numbers in brackets are their record numbers in the GEDCOM. And what you'll see here is a concatenated bit string, which we've accumulated based on the gender as we jump through each hop in this traversal. So we actually get more paths than this. But the query behind this will filter out any MMs here, which would be male-to-male transmission. So we're left only with the X chromosome inheritance. We have again here the Ahnentafel. Now, one of the other concepts I want to introduce here is called ORDPATH. So as you traverse this graph, you can accumulate, using that reduce function, the record numbers of the ancestors as you go along. And this Dewey is a term that was introduced in the ORDPATH developers. It's kind of based on the Dewey Decimal System. And ORDPATH is a concatenated bit string, which has the advantage of sorting in a hierarchical way. So if you were to take this concatenated strings here and sorted that alphabetically, it would not put you in pedigree order. But what I mean by that is here we have the generations, but even within the generations, we have the siblings lined up properly. So ORDPATH is a pretty powerful thing, and there is a specific function in the Graphs for Genealogy plugin that allows you to use this throughout the analytics. For those who are interested, there will be a reference here to the original O'Neill paper on this. And some of you who use SQL Server may be familiar with this as the hierarchy ID data type in SQL Server. So one of the big advantages of graphs is the ability to do common ancestor searches. So the key thing here is two arrows here pointing towards a common ancestor. And on either side of that, on one side you have me, and on the other side we have my second cousin. So we're both traversing through our graphs up to 15 generations here to try to find that common ancestor or ancestor couple, and then you collect their names and return that. So this is a very quick query in a graph database, but there's more than just getting the common ancestor that you can do here. So if we look here, we can have two traversals to this common ancestor, up this way, path 1, or up this way, path 2. And what we can collect along the way is the length of those two paths and how many common ancestors did we find at the end of that path. So this can then be represented in a concatenated bit string. In this example, it would be 2, 2, and 2. And there is a set of nodes that you can look this up using an index and find out that this is a first cousin. So similar examples here of different bit strings, and the relationships will come out. The other thing that is in this lookup table is the data from the Shared Centimorgan project. So you can also get that data for specific relationships when it is in the Shared Centimorgan project. So sometimes it's more complicated. So here's an example of a distant cousin and me and a family tree. And it's a bit confusing because we're related in two ways, as a fifth cousin and as a half fourth cousin. So the graph here gets very muddled up here because the lines overlap, and it's kind of difficult to figure out with this kind of a genogram. So an easier way to do this is with a graph shown here. Now the key factor here is my great-great-great-grandfather married sisters. The first wife died, and then he married her sister. This produces a bit more complicated situation. We have the graph going up to that great-great-great-grandfather, and then another graph going back another generation to the common parents of these sisters. So that produces these concatenated strings for the half fourth cousin and here, and from this person, and the fifth cousins relating to these ancestors. Of course, these brothers here are not half brothers, but rather they're three-quarter siblings because of this scenario. So it can get even more complicated. This is one of my DNA matches down here, and I'm up here. And this particular set of pedigrees has 4 common ancestor couples. And that's because in our two graphs, we have 5 different points where the family tree splits. This kind of thing ordinarily would be a pretty difficult thing to sort out, but in a graph database, this query runs very quickly and quickly shows you the 4 ancestor couples, and then you can create the visualization as you see here. So this is one of the real strengths of a graph database. Another problem that you might encounter is having all of these DNA matches in your data and wondering, do they have a common ancestor? So it's a rather complicated cipher query, but again, in the Graphs for Genealogy function, it becomes a simple call listing the record numbers of these ancestors, and out pops the common ancestors up here. So this is actually also pretty handy. Now, Paths for Genealogy has many user-defined functions dealing with MRCAs. And these are used in many of the different reports, depending on the circumstance, which one of the functions you need to use. So many reports have common ancestors in them, sometimes up to hundreds of them in the reports. There are other pedigree functions we're not going to talk about in detail here, but just to let you know that they are there. We talked about the X inheritance. I particularly like the double cousins one. I have well over 300 double cousins in my database, which really surprised me. In retrospect, it shouldn't, given the fact they were coming across the frontier and married brothers and sisters across the next farm. Another feature is for the nodes, we populate them with a property giving the X chromosome genetic distance. About 5% of your X matches from family tree DNA are actually not tenable based on the family tree, but family tree DNA doesn't know that. And so that's an error rate that you can easily see with this. So another pedigree function is pedigree completeness. That's a very easy thing in graphs for genealogy. Now remember this pedigree here. The other thing that we can do is calculate the correlation of relationship, which is not such an easy thing to do. And there are two functions for this. One is just a single value where you would enter the numbers of these people down here and it would spit out the correlation of relatedness. Another report will give you the details. So here's me and here's that cousin, and it will then show you the common ancestors and the relationship that that single ancestor creates. So here I have two, half-fifth cousins, which adds up to a full fifth cousin. Here we see the path links, the genetic distance, and then the computed correlation of relationship. This report also will estimate based on that and the expected, total DNA. It'll give you the expected DNA. In this case, that number is actually within the range of the shared project, but it's actually a lot less than the 82 centimorgans which were between these two matches. And this is actually not an uncommon thing when you're dealing with these distant relationships. And that raises some interesting questions about the shared centimorgans at distant relations, which we're not going to get into today. All of this is done with a very simple command here. Again, the user-defined function. And the other thing to note in this report is it gives a little educational material. It gives some references to sources, and all of the reports will have the database that's been queried. This is my AVITS database. Now we're going to talk about adding additional graphs to our database. When you do an extra one, you really have to pay attention to optimizing your graph schema. You also have to have a relationship that links the two graphs. And then after you do that, you need to do some optimization to, make your queries perform well. So when you've properly done this, which I hope we have, you're meticulously managing provenance of the data. You will notice that there's very little change in the performance as you add more graphs or more data. That's one of the strengths of a graph database, which we could talk about in the discussion if you want. You'll also get dramatically better analytics and more discoveries because you've got more connections. This is also an opportunity to engage new domain experts, to bring in some of our smart genealogists to add new graphs and new functions. And if they have their own applications, it can be perhaps integrated with them, with the graphs for genealogy. So what's the schema look like here? Well, this is a cartoon of that. We have our person nodes and others coming from our GEDCOM. We have our DNA matches and our segments coming from family tree DNA data, and we connect these together with the relationships shown here. Now, one of the major efforts in this project has been to optimize the schema so that ordinarily in a graph, you might traverse from the person through the DNA match over to the segment. But by taking the record numbers from the GEDCOM and adding them to the DNA match, you can now make the queries simpler. You can start your traversals here instead of here. And that adds a great speed. There is a cost to doing this, which is it has more data in the database, so that will increase the size of the database. But that's rather trivial compared to the tremendous improvements in performance that you'll get by enhancing the graph in this way. The database actually, then what does it have in it? In this case is my Stinnett surname project, which brings in 66 kits. And the GEDCOM has, over 34,000 people in it. The DNA matches that this generates are almost 250,000, which is well over 10% of what's even in family tree DNA. It has 356,000 segments. It has the haplotree. Many of you may remember the announcement a few months ago that it passed 50,000. As of yesterday, it was 54,319. It also then has relationships between the kit and the person here, between the kit and the match here, and the number is shown there. And then it has these match segments where you have the match to the segment. And then this is one that is produced by the software, which is basically in common with matches, which allows you to link the different matches together using that. This database, which has this amount of data in it, is 825 megabytes in size. So the family tree DNA integration of autosomal DNA really had a specific strategy behind it. You wanted to preserve all of the granular detail from the source files when you create the kit, DNA match, and segment nodes. You then link these together. You then integrate in triangulation group curated data. And you do the same with a linkage that is curated by the genealogist between the GEDCOM and the DNA. And then you start enhancing the graph. So the benefits of this is that you have traversals across graphs. You can also begin to enhance these graphs, as I just mentioned, by propagating some properties. And you can start to create supernodes, such as triangulation groups or this monophyletic segment sets, which I'll talk about in a minute. Let's take a look at a couple of things that we can do here. First of all, I just want to point out the supernodes here. The haplotree has blocks at the branch points, so sometimes these are called branches. I call it a block because it is really a supernode that subsumes a lot of variants or SNPs in it. Also, the triangulation group subsumes many different segments. Now, nodes can also have multiple labels. So this DNA match might be a DNA tester. So you could give that node a second name, and then you can use what are called GRAS files to create styles, that what gets displayed in the node, how many properties. The advantage of a GRAS file is you can have more than one property. You can change the color, the shape. GRAS files are analogous to the CSS files for those of you who are familiar with HTML. So now I want you to kind of imagine with this kind of a graph, what kind of traversals you might do. And this starts to get us into our graph thinking. And you really have to kind of put on a different thinking cap and you start thinking in graphs. So I'm going to give you some examples here of how you can use the graph traversals to the advantage of our genealogical questions. We're going to start with cluster matches, in which you take the matches and you use your in common with matches to create a group of matches. And then you can also look at the segments that are associated with them. So this began in my own research quite a few years ago, looking at clusters of cousins who are all linked by their in common with DNA test. And then you link them to the family tree. So that you now have the DNA linked to the family tree. And in this case, these cousins link back to first cousins to a grandparent, second cousins to great-grandparents, and the third cousin to great-greats. And then at that point, we're doing manual looking at the segments and trying to relate them back to these folks. So the question is really now, with a fully developed graph environment, can we make that easier? Here's a figure which may look somewhat familiar to you. It's very much like the old Ancestry.com DNA circles. And this is derived by getting a cluster with these matches who are shown on the periphery, all of whom have a record number, so we know who they are, except this one. So this person really becomes a person of interest and somebody you're going to want to investigate and do some traditional genealogy research with. Now, we know that from our experience with DNA circles that these people may not actually share segments, but collectively, they do share a probably common ancestor. So we can ask the question of, do these people really share common segments? And you can do that by exporting the segment data. And many of the functions have an ability to create a DNA painter file. But you can also look at it in a different way. Here we see the DNA circle in blue kind of in the background here. And this is all of these segments that are associated with those matches. And all of them do have a shared segment, but you can see that some of these have lots of them and some of them have very few. This kind of a visualization is done with a third-party application called GraphRx, which I've been partnering with to try to develop some of these visualizations. Another way you can now start to add another graph to this. This is an example where we have the family tree, then the DNA nodes, and then the segments shown here. Here we have a family tree coming down several branches to matches, which are the DNA results from these people. And then we have their linkage to the segments down below. Now, and here we have, all of the in common with connections between these things. And we also have a segment sequence relationship down here because these are sequentially ordered segments down here. And they're actually a rather small segment, which corresponds to a triangulation group. We can get rid of those extra connections at those levels and just show the direct connection between the ancestor through the match down to the segments. And this kind of illustrates how a triangulation group really works, that these people converge on a set of segments that are in a discrete region of a chromosome, but they actually may have slightly different but overlapping segments that make up the triangulation group. So the monophyletic segments, which we saw at the bottom of that graph, are actually not that common. The fact is that there are many overlapping segments and only a small set, less than 1% of those, can be mapped back to a common ancestor. So one of the reasons I call them monophyletic segments is because this sort of is like a phylogenetic tree. These segments only relate back, and these segments are actually quite specific for this family branch, unlike all the other overlapping segments that are not. So here's an example of using ORDPATH along with the segment data. So here we have a segment that is the same, and it is seen in 3 different people here. And you can see quite clearly how that comes down the family tree in different branches. So this is making use of a combination of ORDPATH and a family tree with specific segment data. So I'm hoping this will be helpful in tracking specific segments through branches of the family tree. We're trying to get at triangulation groups, so we can take the DNA matches, relate those to the family tree through triangulation groups up to the segments. So we're going to look at triangulation groups now. And one of the things you can do when you pull that data out is create a file which can be pretty seamlessly uploaded to DNA Painter. And in this case, we've kind of hijacked some of the functionality here. This up here are actually the boundaries of the triangulation groups. And here are the match pairs, because each of these segments represents a pair of people who share a segment. And so these are listed here, and they are related by the color code here to specific people who are their common ancestors. So we really see a whole lot of things here. We see that these things line up, and we can relate them back to common ancestors. The other thing that this points out to you is the caution you should observe by looking for these pileup regions. So this may be a little suspect by it being aligned with a pileup region. But the basic point here is that we're bringing together the family tree, the shared matches, and the segment data all in one port. And you can see this visually like this, or you can see this in an Excel kind of report which shows you that pair of the person whose kid it was and the match, their relationship, their common ancestor, the specific segment data that exists there. Then you can also roll this up so that for any individual, you can see the triangulation groups that they have. And you'll notice that for various people, they inherit those triangulation groups in a different pattern, which really starts to create the autosomal haplotree. So let's talk now about clusters a little bit more, the match by segment clusters, in which we're just looking at this particular area of our graph. You can use that information to do a number of analytics. Neo4j has a plugin called Graphs Data Science that has a number of community detection algorithms in there, like the Levin modularity optimization page propagation algorithms. This display is in the GraphRx again. It also has a Levin algorithm in it, and that's what you're seeing here. The colors here represent different communities within the graph. And I can just tell you, because I know this data, that those communities align with branches of the family tree. So you can also, with this, identify the segments that are associated with each community and display those in other ways too, including DNA Painter. The other nice thing about GraphRx is this rendering here is actually in 3D, so you can rotate this image around. And they also have the capability of doing virtual reality, so you can really view it in real 3D. So another set of queries involves the fact that in family tree DNA, about half the matches give you a list of your ancestors. And Neo4j supports full text indexing. So you're able to find ancestors' surnames from these kits and then link them to the segments as well. You can also do wildcard searches as well. That has quite a few advantages. You can search for multiple surnames, and then this is just a few lines out of the report. And what you can see here, this is my Stinnett family, which also has Kent and Calverts in one of the branches of that family. And it's very easy to see these combinations in the report. So this report actually had over 2,000 lines in it, but in a very small number who had people who reported all of these ancestral lines. And obviously, if those are new people to you, those are ones you're going to want to focus into. So you get this matches of the surnames with the source, what kit did these come out of, and also the shared centimorgans and the segment count. You then get another report, which has a report of the in common with matches of these people. So you can see the cluster of known matches who line up with the new people and the MRCAs associated with them. Much like the DNA circles, many of these do not have shared segments, but when they do, you also get a report that will show those. So that's kind of where we are at this point. I do want to remind you about an invitation to maybe get involved with this project by going to this website and then kind of reading what the options are. So I want to review what I think may be the future of this field and what those opportunities might be and where you might become interested. So we can do quite a bit more work. There's great opportunities with the haplotrees. Fan groups is another big area. I'm going to show you some examples of these, what we might do with endogamy, and then some future visualization challenges. So there is Y-DNA data in there. So this is just a simple example of a starting point here at RDF29 and then traversing the graph and going that way, going this way, and then out all the branches. These are the kits that are on these particular nodes on the tree. I'm interested in these guys over here in my Abbott's family, and I can see that, there's some other people who are closely linked here. And it turns out that the main difference between these guys and these guys is when they did their testing. And at that time they tested, they weren't doing testing for these SNPs. But this gives you a pretty nice quick visualization of how the tree is structured. So fan groups or family, friends, associates, and neighbors is another big opportunity. Here's a census record that I encountered years ago. Didn't fully at first understand what it is. Here's that William Averett who married two sisters. My great-grandfather here, Anderson Averett. But there's all these other names I didn't understand when I first saw this census 20 or so years ago. So here's that family tree again. Here's my great-great-great-grandfather, the two sisters. The first sister had a child with him and then died. The second sister here had a previous marriage and had a son there and then had 4 children with him. And the third wife had a previous marriage with 2 children, but had no children by him. So now we come back to the census record and we can begin to connect people together. And we're in essence now creating a graph that links the family tree to specific items in a document. You can also do this with other kinds of documents, as in photographs. This is my great-grandmother who lived well into my lifetime. And this is a Thanksgiving picture from the 1950s. And what you'll see here is that I've labeled each of these people, and that is linked to the family tree data. And so now you can create from the family tree data and from the graph, you can say that this Joseph Smith, his father was William Smith, and his wife was Willie Davis, and her mother was my great-grandmother. So now you have everybody in this picture linked to a graph of them. That is a fan group. Now you can use these fan groups in many ways. So this is a capability that could be much further developed. I have this on some personal software at home. This could be brought into the graphs for genealogy functions. Another area would be geography, and we have done some of this with GraphRx in my data. This doesn't happen to be it, but GraphRx has geospatial and time series, so you can link a graph of something like a family tree to a map and create migration patterns or locations of events. You can do that in this format as well. So as I mentioned before, I think there are a lot of other opportunities of how one can use other visualization tools like DNA Painter, and I'm kind of talking now with Johnny Pearl about some of those potential options. There's other kind of charting that could be done. This is one of those through line kind of queries where you have the common ancestor over here. You have the shared centimorgans. You then have the path to the common ancestor. I've de-identified the living people over here. And then you can also produce a dendrogram. So here's in the bottom here, they're marked with red, a little difficult to see, but all of the DNA matches, and only DNA matches are shown at the bottom here. And here is me, and we all relate back to these common ancestors back here. So this is also a pretty powerful way to illustrate your DNA matches. And like I said, this is very similar to the through lines. One of the areas I'm particularly interested in is, can we use this in endogamous pedigrees? This is a disease from my academic research career. I did research on Friedreich's ataxia. And one of my colleagues up there, Andrew Barbeau, was working with the French Canadian population, which here you can see we have this couple who shares common ancestors, a very endogamous pedigree, and that produced, these children down here, all of whom ended up having Friedreich's ataxia. The question here, those monophyletic segments differ by the start and end positions, that is the crossover points. And I think it could be possible to demonstrate that this person got a monophyletic segment from, say, this branch of the family tree and not this one. And so I'm looking for collaborators for that. Tim and I are talking about his Mennonite project that way, and I have a colleague who has a French Canadian pedigree similarly. So that's a research question. I don't know whether that's going to be possible or not. One of the other areas that I think is ripe for development here is in forensic genealogy. There are lots of networks in the criminal justice system. Law enforcement has networks. The cases have connections. The bodies here, the missing persons there. There's crime scene evidence. There's suspects who, may be associated with each other. And then there's all the forensic repositories. So it's very easy to kind of envision a schema. Right up here is what already is in graphs for genealogy. And the question is, can you start adding new nodes here? One of the interesting projects that you could look at is the Panama Papers. The Panama Papers used Neo4j graph database, and journalists from around the world began putting data into that. And after a critical mass of data was put together, they could very easily connect all of the money laundering folks to a company in Panama. And this brought down the Prime Minister of Iceland and a whole lot of other people by doing that. I think something very similar is possible with forensic genealogy. So in summary, graphs are everywhere, and we've made an effort to optimize graph environment for genealogists. You can get kind of multiple capabilities in one package, and I think this is going to be well suited for your personal research and for those of you who do it for your client research as well. So I hope that you enjoy this and you use it, and I would welcome all of your thoughts and questions in terms of feedback, suggestions, and hopefully some of you will choose to become involved with this actively. So with that, Tim, I'm going to stop